This is a very hard math problem that my teacher couldn't do after I asked her. Sometimes teachers give their students problems that make no sense, and the student, trying to get a good grade, wastes an afternoon struggling through some honky-tonk hogwash. Like this problem about a quilt so heavy it can't even be lifted by a pair of magical warriors. Other times, a teacher just accidentally gives students a problem way harder than they mean to. For example, there are several stories of students ending up with the infamous Langley's adventitious angles problem for homework. In rare cases, however, it is the student who burdens himself with a difficult problem. The OP mentions in a comment that his friend sent him this problem, so it's not some homework the teacher assigned and was unable to do herself. Although the title does raise the question, could the teacher have done this problem before OP asked her? Alas, we can't know. A set M of real numbers is called a special set if it satisfies the following conditions. Condition 1. For any two distinct elements, x, y, in M, we have that x times y times x plus y is non-zero, and exactly one of the two numbers, the product and the sum, is rational. Condition 2. For every element x in M, the number x squared is irrational. Note that this immediately implies every number in M must be irrational, since the square of a rational number can never be irrational. Then, with these conditions laid out, the problem is to find the maximum possible number of elements in such a special set. At a glance, this looks a lot more difficult than your average high school math problem, but have no fear. According to the comments, this is actually a problem from a 9th grade math competition, so it can't be too hard. Although, if you don't know much about high school math competitions, you might be surprised. One of the defining features of a high school math competition is that they generally don't require any calculus. But what they do require, and what you might only learn a little bit about in a standard American high school math curriculum, is Combinatorics. Combinatorics is a field of math focused on combinations and arrangements of discrete structures. Whether you know about combinatorics or not, at a glance, this problem might not jump out at you as a combinatorics problem. However, there are many clever folks on r/askmath, and this fella wrote up a solution immediately making it apparent that this problem could be pretty easily disposed of with a combinatorial approach. I want to give you a detailed exposition of this graph theory solution to this problem, so if you want to give it a try yourself, now's the time to pause and give it a go. Now, let's get into the solution. One of the principal objects of study in combinatorics is what are called graphs, and not the XY plots we make in the Cartesian plane. No, in combinatorics, a graph is a structure consisting of vertices and edges that join pairs of vertices. And a graph is often used to represent a relation on a set of objects, such as people at a party. The vertices of the graph are the people at the party, and they're joined by an edge if they are friends. If they're not joined by an edge, then they are strangers. We see here, for example, that Sakura and Rock Lee are friends, but of course Rock Lee and Warren G. Harding are not. There is another common way to model a situation like this, which begins with what we call a complete graph, where every pair of vertices is joined by an edge, so the graph is complete in the sense that it has every possible edge, but then we color the edges according to the relation they represent. So in this situation, we might make an edge blue if it joins two friends, and make it red if it joins two strangers. This way, every pair of people is joined by an edge with the color to indicate if they're friends or not. And this sort of model turns out to be convenient for this math competition problem. In a special set M, we know that two numbers x and y either have a rational product or a rational sum, because that's just one of the conditions of these sets. It's one or the other, rational product or a rational sum, just like this model where two people are either friends or strangers. So we want to consider a special set M that's as big as possible. Of course, we don't know how many numbers such a maximum sized special set has, but for each number it does have, we'll use a vertex to represent that number. I'll draw little dots going off this way and that way, showing that we don't actually know how many vertices are in this graph, since we don't actually know how many numbers are in the biggest special set M. For the sake of having an illustrative diagram, we'll assume that it's got at least 3 numbers, and we'll just call these x, y, and z. And we're going to have this graph that represents our big special set M be a complete graph. So every pair of vertices, which represent numbers from M, in this graph is joined by an edge. I can't draw them all because I don't know how many vertices there are. However, to represent this key feature of numbers in M, we'll say that in our graph, two numbers are joined by a blue edge if their product is rational. And the other possibility, their sum being rational, will be represented by a red edge. So this is the key for the colors in our graph. If two numbers have a rational product, they're joined by a blue edge. The only other possibility, based on the conditions of the problem, is that the two numbers have a rational sum, in which case they'll be joined by a red edge. Keep in mind, it's totally possible for two numbers to have both a rational product and sum, like plus or minus root 2, for example. It's just a condition of our problem that the numbers in the set M satisfy this property of only one or the other being true. Now notice in this little sort of arbitrary representation, we have what's called a triangle. However, this triangle doesn't consist of only a single color. Two of the edges in the triangle are blue, and the other edge is red. Now, it turns out, based on how we've constructed this graph, according to the properties of these special sets M, it's actually not possible to have a triangle of a single color. So I'm claiming that in our graph, even though we don't know how many vertices are in it, based on how we've constructed it, it's not possible to have a blue triangle. Those would be 3 numbers who all have rational products. And it's not possible to have a red triangle. Those would be 3 numbers that all have rational sums. To see why we can't have these things, let's demonstrate that a contradiction results from either one existing. Here's what a blue triangle would look like, and this of course would mean that the product of any 2 of these numbers is rational. So x times y, as well as x times z, would both be rational numbers. Of course, if xy and xz are rational, then their product is certainly rational as well. And we can rewrite their product like this. Combine the factors of x to get x squared, and then let y and z pair off as well. Now, like we just said, this is a product of rational numbers, so this, which is just the product rewritten, also has to be rational. But this is a problem, because we also know why z is rational. However, by condition 2 from the problem, we know that every number in M has a square that's irrational, which means this x squared right here must in fact be irrational. But this then is an impossibility. We can't have an irrational number multiplied by a rational number produce a rational. Just for example, if we could multiply the square root of 2 by some rational number a over b to get some other rational number c over d, then we could isolate root 2 and write it as bc divided by ad, which would mean that root 2 is rational. So again, an irrational times a rational can't be irrational. This is not possible. This establishes that we cannot have a blue triangle in our graph. Now, a very similar line of reasoning is going to prohibit a red triangle, where all the pairs of these numbers would have a rational sum. The existence of this red triangle would tell us that x plus y is rational, and it would tell us that x plus z is rational. But of course, if these two numbers indicated by those red edges are rational, then so too is their sum. But we can rewrite the sum, combine the two x terms to get 2x, and combine the y and z to get y plus z. Y plus z, of course, is rational, since they have a red edge between them. However, 2x has to be irrational. That's because x has to be irrational. Remember, we said this before, that since every number in M has an irrational square, every number in M must itself be irrational. And you can't double an irrational number to get a rational. Hence, 2x has to be irrational, just like x is. But then, an irrational number can't be added to a rational to produce a rational. So we have this expression, which has to be rational because it's a sum of rationals, but it's equal to this expression, which can't be rational because it's a rational plus irrational. This then clearly prohibits the existence of a red triangle in our graph, since it leads to this contradiction. Now, what we've been calling a triangle is just one example of an odd cycle. It's clear visually why this is called a cycle, and it's an odd cycle because it has an odd length, 1, 2, 3. And it turns out that just like a blue odd cycle of length 3 and a red odd cycle of length 3 can't exist in our graph actually can't have any monochromatic odd cycle. Our graph can't have a blue odd cycle, and it can't have a red odd cycle. The arguments we use to show that red triangles and blue triangles can't exist can be generalized to show that in general we can't have a blue odd cycle or a red odd cycle in our graph. Just for example, to see how the generalization could work, let me show you that no blue cycle of length 5 exists. Just like in the triangle argument, we'll take the product represented by every edge except one. So we have the product AB, the product AC, the product BD, and the product CE. And we're leaving out this one at the bottom. Of course, because all of these edges are blue, this is a product of rational products. AB is rational, AC is rational, and so on. However, we can then rewrite this product. Let's bring an AB together, right there. And then we also have AB, we'll bring those together too. We also have DE, which of course we know is rational. And all that leaves behind is two factors of C, so C squared. Then, just like in the case of the triangle, these equal expressions give us our contradiction. This is a product of rational numbers, so it has to be rational. But it's equal to this. And this is rational times rational times rational, so this whole thing is rational. But then at the end, of course, is C squared, which we know is irrational, because the square of any number in M has to be irrational. We can't have rational times irrational equals rational. So this clearly is a contradiction. Okay, so hopefully we're in agreement that our graph has no blue odd cycles and no red odd cycles. But these two facts mean that our graph has to be what's called four-colorable. Now, this is in reference to coloring the vertices, not the edges. And what it means for the graph to be four-colorable is that it's possible, with no more than 4 colors, to color the vertices of the graph so that no two adjacent vertices, that is, vertices joined by an edge, no two adjacent vertices have the same color. Here, for an example, is a coloring of a graph that only requires 3 colors. You can see here are 2 vertices that have the same color, they're both purple, but they're not adjacent. Over here we have a triangle, 3 vertices that are all adjacent to each other, which forces us to use 3 colors. But for the rest of the graph, we don't need any new colors. But now what you have to remember is that this hypothetical graph G representing our special set M is a complete graph. Remember, we said that every pair of vertices will be joined by an edge, and we'll just color them according to the relationship they have. Now, if you're trying to color For a complete graph, you can only have as many vertices as you have colors, because in a complete graph, every vertex is adjacent to every other vertex. In this complete graph on 4 vertices, for example, if we color one vertex blue, no other vertex can be blue, because they're all adjacent to this one. If I color another vertex red, no other vertex can be red, because they're all adjacent to this one. Clearly, in a complete graph, if we have n colors available, we can only have up to n vertices. With all 4 of these colors available, I could also color a complete graph with 3 vertices, or a complete graph with 2 vertices, or a trivial complete graph with a single vertex. But if all I have is 4 colors, I'm not going to be able to do anything bigger than this one. So if our graph representing a special set M has to be 4 colorable, which I'll justify in a minute, if it has to be 4 colorable, then it can't have any more than 4 vertices. But of course, the number of vertices is the number of numbers in the biggest special set M. That means the answer to our question, the maximum number of elements in such a special set, has to be no greater than 4. Now, it could still be that the maximum number a special set M can have is actually less than 4, but certainly it's no greater than 4. Now, let's make sure we're clear on why the graph has to be 4 colorable. It's because of a classic theorem of graph theory telling us that a graph is bipartite if and only if it has no odd cycles. For a graph to be bipartite means that we can arrange it in 2 parts, so that every edge goes from one part to the other part. For example, this square is a bipartite graph, which we can demonstrate by putting its vertices into 2 parts, and you can see that every edge goes from one part to the other part. A has an edge going to D, C has an edge going to D, and C has an edge going to B. This is the same graph as this, just written in a way to make it clear that the graph is bipartite, and you can see every edge goes from one part to the other. And like the theorem says, a graph has this property of being bipartite if and only if it has no odd cycles. Link in the description to my video proving this famous theorem. Our graph modeling the special set M is definitely not bipartite, since it's a complete graph, and no complete graph is bipartite except for these 2 really small ones. In all likelihood, our graph does contain odd cycles. However, we know that its edges can be colored blue and red in such a way that the blue part doesn't contain any odd cycles, and the red part doesn't contain any odd cycles. This means we can imagine our graph is composed of 2 subgraphs. A blue subgraph that's bipartite because we know it has no odd cycles, and a red subgraph, which we also know is bipartite because it has no odd cycles. And then finally, any bipartite graph is guaranteed to be 2 colorable. Remember, the whole definition of a bipartite graph is that it can be written in this way so every edge goes from one part to the other. So all the vertices in one part can get color 1, and all the vertices in the other part can get color 2. Clearly, any bipartite graph can be colored with only 2 colors. So that means our graph modeling the special set M with a maximum number of elements has a blue section that can be colored with only 2 colors, and a red section that can be colored with only 2 colors. And so the entire graph is absolutely 4 colorable, since a 2 coloring of the blue subgraph and a different 2 coloring of the red subgraph could be combined to get a 4 coloring of the whole graph. And so indeed, a graph modeling our special set M cannot have any more than 4 vertices, because it's a complete graph that's 4 colorable. Like we said, this doesn't mean the answer to the question is actually 4. We need to find the maximum possible number of elements in a special set. We know that it can't have more than 4 elements now, but we don't know if 4 is itself possible. We could show that 4 is the answer, though, if we could construct a special set M with 4 elements. I'll give you a minute to pause the video if you want to give that a try. It ultimately just comes down to constructing some numbers that are combinations of wholes and irrationals, intelligently so that they add and multiply in the way necessary to satisfy these conditions for being a special little set. The OP already had 4 in mind as his answer, and he gave an explicit construction of a special set M with 4 elements. You can verify that the conditions for being a special set are satisfied by this set of 4 elements. It doesn't take too long to verify. Just for example, if we add these first 2 numbers, it's certainly an irrational sum because 1 and minus 1 cancel out, and 2 times root 2 is irrational. That means their product had better well be rational, and in fact it is. These 2 numbers actually are conjugates, so if we multiply them together, we would get the difference of the squares, meaning we would get 2 minus 1, so 1, which of course is a rational number. And so 4 indeed is the correct answer to what apparently is a 9th grade math competition problem. I'm a big graph theory fan, so I really got a kick out of this solution, and I hope you did too. If you really want to show off your love for graph theory, check out mathshin.com, my math fashion brand. It's the only place that you can get math clothes and accessories that are obviously about math, but only if you know math. This, for example, is a graph theory shirt featuring Leonard Euler walking into the city of Königsberg, which is referencing the famous Bridges of Königsberg problem that birthed graph theory. There are other awesome designs too. If you like this one but don't want a big piece of art on a shirt, you can get it on a mug and magnets and other things as well. So check it out. I'd really appreciate your support. That's mathshin.com, link in the description. And be sure to subscribe for more of the swankiest math videos on the internet.
I'm unstable, I'm feeling hard to keep the cable cut and untuck the cable. If Texas Instruments don't reply, I think this time it might be fatal. Wish to sell my own fake, cause I'm jaded.
Hate the odds that I calculated.
Press and pull and pray and push it all the way through the whole blue planet.
Planet faded.
Sun